Swayam Prabha. Digital India. Educated India.
Hello everyone. As all of you are aware that we are discussing the idea of modes in a device, and last couple of lectures were on introducing the modes and how to derive the expression for the modes in a device. So today we will go a bit more into the details of this new notion, the notion of modes. And as we are aware that this quantity in the current expression, this quantity which we first saw in the current expression is defined as the modes, and it depends on primarily two parameters. One is the gamma E, and second is the quantity dE, and then we also have a constant pi by 2 in the expression for the modes. So this dE is essentially the number of electronic states per unit energy in the device, and it is defined as, so if we collectively define it as for 3D, 2D and 1D, this is defined as volume times G3D E, where G3D E is the density of states for the 3D material, area times G2D E, G2DE is the density of states for the 2D material, and length times G1DE. Now we also saw that in order to derive, or in order to actually see how this expression, how this quantity looks like, we need to know what is the gamma E in the device, because we already know what is this dE parameter. We just need to know the gamma E parameter, and in order to calculate this gamma E parameter, we started with a description of a 2D channel. This is how it looks like. This is just a slanted view of the channel. We can also sort of take it to be like this. We have a source, we have a drain, and we have a 2D channel. There is a length, and we also have width, which is denoted as W. In this kind of setup, we saw that in order to calculate gamma E, or in other words, in order to calculate tau E, which is essentially h bar by gamma E, we need to find the ratio between the stored charge in steady state divided by the current. So the ratio of the stored charge and current, this ratio is essentially the parameter tau E. In our description in the previous class, we had Q in the denominator of the right hand side. Okay, this is what we had, and please also keep in mind that this was true when this was true in the case of a thought experiment that we did, and in our thought experiment we applied a large voltage across the device. So across the device, near equilibrium conditions are not true, but in the contacts the near equilibrium conditions are still true, because the contacts are bulk contacts, large contacts, and lot of electrons are available there. The number of electrons is huge. So any application of voltage quickly brings, or even after any application of voltage, the electronic population is quickly in the equilibrium state because of the inelastic scattering in the contacts. So, this is what we had, and after this what we saw was that in a ballistic case, ballistic means when the electron is starting from the source terminal going directly to the drain terminal. In that case, this expression tau e actually turns out to be L divided by V x, means velocity of electrons in x direction, and positive means positive x direction. Positive x direction is the direction from the source to the drain, okay, and average of this, average velocity of electrons in the positive x direction in the device. That's what we saw, and generally in order to calculate this average Vx plus, or I would say in order to calculate Vx plus E, Vx plus E is the velocity of an arbitrary electron that is starting from the source towards the drain, and we can, in a 2D channel, we can assume that the electron is starting at an arbitrary angle theta with the x axis, and this theta can range from minus pi by 2 to plus pi by 2. This is the range of these theta angles. Vx, so the velocity, if the electron is starting with velocity Ve, the velocity in the positive x direction will be Ve cos theta, okay, and this Ve actually comes from the relationship of the energy of electron with the total energy of the electron with the kinetic energy of the electron. So, which means that this Ve is equal to, please keep in mind that generally when we use when we treat electron as a classical particle or like a particle, we need to take we need to have the parabolic band structure, which means the EK relationship should be a parabolic relation. E should be equal to EC plus h bar square k square divided by 2m star, and we need to have, instead of electron mass, we need to have the effective mass. So, this Ve will be square root of 2 E minus EC divided by m star, okay, and the average value of this would be the average value of this. Ultimately, this turns out to be the average value of cos theta, which is, as we saw in the last class, is 2 by pi V E. So, this is what we have now, and where V E is given as by this expression, okay. So, this is the ballistic case, and electrons are, which means that electrons are not dissipating, electrons are not changing any pathway during their transport from the source to the drain, okay. So, now with this we can see just one thing that needs to be kept in mind is that generally when we deal with electrons, we have valence band, we have the conduction band, and if the electron is sitting somewhere here, and if this is the reference energy level, let us say the E reference is somewhere below the valence band, which is the reference energy level is generally taken to be the 0 energy, then the total energy of the electron sitting at this energy level will be E, and this fraction of this energy will be the kinetic energy. So, which means that E is written as EC plus half m star V E square. Okay. Also, as we saw in our previous discussions, that in the conduction band, the EK relationship can be written as E equals EC plus h bar square k square divided by 2m star. Okay. So now we are in a position to explicitly calculate what is the modes, number of modes in a device. And so please keep these two expressions in mind. Generally near the top, near the bottom of the conduction band, the bands are parabolic and this relationship holds, and the amount of energy that is in excess to the bottom of the conduction band is the kinetic energy of the electron, and that is given with this relationship. Okay. So now let us come back to the expression for the current, and that is how it looks like. The current in the device, any arbitrary device, looks like this. This is the integration of gamma E pi times dE by 2 F1 minus F2 dE. So this factor ME, this is the ME, and a two terminal and in a 2D device, this dE is given as, in a 2D device, dE is area times G, the density of states in 2D device, G2dE, which means area times m star divided by pi h bar square, and gamma is given as h bar by tau, which is essentially h bar by L divided by Vx plus, which is equal to h bar by L 2 by pi into V E. So if we put this value of gamma E and this value of dE, which is essentially W times L times m star divided by pi h bar square. So this value of dE, it ultimately gives us the number of modes to be h bar by L 2 by pi times VE times W times L m star divided by pi h bar square times pi by 2. So this pi by 2 and 2 by pi cancels, L h bar h bar. So what is left is something like this. Ultimately the modes can be written as, if we sort of eliminate all these redundant things from here, it is ME equals, what is left here is W times m star divided by pi h bar square, sorry, h, now we are only left with h bar, not h bar square, W times m star divided by pi h bar times VE, which is also m star pi h bar, VE is essentially square root of 2 times E minus EC divided by m star. So, this is the number of modes in a 2D channel, and as we discussed in the last class, that number of modes in a channel is essentially the number of conduction pathways in the channel that are there, and number of conduction pathways means that that these are sort of lanes in the channel that are available for electrons to conduct essentially. Okay, so this is what we have. This is for the 2D channel, and this is all we have seen. Finally, this is another way of writing the number of modes in a 2D channel like this. So, this expression for the modes W times m star divided by pi h bar times this is equivalent to that expression, and that is also written as W times m 2D E, number of modes in a basically m2d E is the number of modes per unit width of the channel. So, this was the case with a 2D channel, and this expression is exactly equivalent to this expression. So, number of modes is in a 2D channel is, in a more formal way, it can be written as number of modes times W times number of modes per unit width, and where number of modes per unit width is h by 4 average velocity of electrons in the positive x direction times d to d E. Okay. Similarly, the similar expression will hold true for 3D channel as well. So, for 3D channel, for a 3D channel, total number of modes in the channel would be W times m 3D E, and here in addition to W we will also have length, or we will have area times m 3D E, where this m 3D E is the number of modes per unit area, and for a 1D channel total number of modes in the channel would be just m1D E, and that will be h by 4 Vx plus E times d 1D E, where d is essentially equal to g 1D E, density of states in one dimensional channel. So, this is what we finally obtain. So, here d and g, which means here d with subscript 1d is essentially the density of state in a 1D channel, d subscript 2d is the density of states in 2D channel, and d subscript 3d is density of states in a 3D channel. Okay. So, this is so we are not explicitly deriving modes for 3D channel and 1D channel. I would recommend all of you to try this derivation, and this is pretty much similar to the derivation that we did for the 2D channel. In 2D channel, things are I would say more can be explicitly visualized, and that is why we started with a 2D channel, because the length and width we can easily picturize in our minds. So, so finally, what we can the way we can sum it up is that the electron density in the device in equilibrium, or the total number of electrons in the device in equilibrium, can be written as dE times F1 plus F2 by 2 dE, where dE is the number of electronic states per unit energy in the channel, and the current can be written as this constant 2q by h integration over ME times F1 minus F2 times dE, and where we now know explicitly the forms of dE and ME. dE comes from the density of states, and ME comes from the modes in the channel. So this is essentially the idea of the modes in a channel. Now there is an interesting way of looking at the modes in the channel, and that's what we'll do now. So if we sort of start with this expression, if we so for example, let's take the case of a 2D channel. So the device, our device looks like this. We have the length, the width, the source contact, and the drain contact. This is the channel. The number of modes in the channel is given as, from here, W times h by 4 average velocity in x direction. Please work out these derivations on your own as well, because until you do that you won't understand that properly. So if we write these positive velocity in x direction, the expression for this is 2 by pi square root of 2 times E minus EC divided by m star, and this d to dE is m star divided by pi h bar square. So putting everything together, we have ME, number of modes in a 2D device, is W times h by 4 times this. Now if we assume, or if we assume, I won't say assume, because that is generally the case in most of the devices near the conduction band. We have parabolic relationship between E and K. So the EK relationship can be written as E equals EC plus h bar square K square divided by 2 m star, where K is the wave number of the electrons, which means E minus EC is essentially h bar square K square divided by 2 m star. So if we put this value of E minus EC into this expression, the expression of modes, this will further simplify to W times h by 4 times 2 by pi into E minus EC is h bar square K square divided by 2 m star into m star. So 2 will go away, and here we have m star by pi h bar square. Okay. So this is the expression for the number of modes in the 2D channel. this on further simplification becomes W times h by 4 times 2 by pi. Now everybody comes out of the square root. So it is h bar k divided by m star multiplied by m star divided by pi h bar square. M star and m star go away, and h bar finally what we have is this W times h by 4 times 2 by pi into k into 1 by pi, and h bar can be written as h by 2 pi. So this further cancels out, pi and pi, 2, 2, okay. So what is left with us is W times k by pi. So if we divide and multiply by 2, this is what is. Now please recall from the basic quantum mechanics that according to the wave particle duality, if the wave number of an electron is k, its de Broglie wavelength is lambda b is 2 pi by k. Okay. So if we have this here, it becomes W times 2 divided by lambda b, or W divided by lambda b by 2. So this is actually the number of modes in a 2D device, in a two-dimensional device. Number of modes in a two-dimensional device is actually width divided by the half de Broglie wavelength of the electrons. And now this is an interesting result. What it says is that the number of modes in a device is essentially the number of half wavelengths that can fit into the width of that device. So it essentially means that that it is essentially this number of half wavelengths, where this is lambda b by 2. So what it says is that the width of a conduction pathway, or so to say width of a highway or a lane in the channel, is essentially the de Broglie wavelength divided by 2. And that's why, so what it says is that in order for an electron to go through from to travel through the device, it needs at least lambda b by 2 space. So it is not a point particle, it is like a wave. And in more classical sense, if we treat electron classically, it becomes a particle that needs lambda b by 2 space while traveling through the channel. And that's why the number of conduction pathways in the channel is width divided by lambda b by 2 in the case of a 2D channel. And this is an interesting and important intuitive result actually. So please keep this in mind, because this makes the idea of modes more clear, more physically clear to us. Why this idea is important and how this idea is different from the density of states. As you might recall that in density of states, we have the number of allowed electronic states per unit energy per unit volume, and those energy states are discrete energy states. There is no broadening of energy levels, there is no we do not say that electron is occupying a certain space, but while electron travels, because of the finite lifetime, it leads to energy broadening of levels, and that broadening is roughly equal to lambda b by 2, which is the de Broglie wavelength of the electron. And or in other words, electron behaves like a classical particle that needs at least or that needs space of around lambda b by 2 while traveling through the device. So, this is an important intuitive result, and finally, this is how we can summarize our results. These expressions are the expression for the density of states in the device, and these expressions are the expressions for the number of modes in the device. And where we have this parabolic band assumption, which is not an unfair assumption in most of the cases, and the velocity, or more precisely the average velocity of electrons, is given by this expression. So, we will discuss about this in somewhat more detail in the next class, and until then I will let you think about the I will let you think more about the intuitive understanding of modes in a device. So, thank you for your attention. See you in the next class.